Okay, this is part 3 of our boundary condition analysis discussion, and in this case I just want to quickly show you a couple of case studies that I've been involved with in my career and talk specifically about the boundary condition selection and some of the choices we made and how that worked out. The first one I'm going to talk about was a model we built in the early 2000s, and I was partnered with another modeler on this, Michelle Smilowitz, who did most of the modeling work and we did this through Acaveo. And this was a groundwater model in Steptoe Valley, which is in eastern Nevada, at the location shown on the map on the left. And this is near, if you look down at the bottom of the map, Ely, Nevada was just at the lower end of this region. And at this point in time, there was a power company that was looking at developing a coal-fired power plant to put in Steptoe Valley, and they were looking at a number of different locations. Two of the locations that were proposed are here and here. And this particular power plant design required quite a bit of water, and so there was a plan to purchase water rights from local ranchers and stakeholders to develop and maintain this particular coal-fired power plant. But in order for this to be constructed, they had to conduct an environmental impact statement to satisfy EPA regulations, and you have to do that for any power plant or any major project like this. And so the model, we were hired to build a model to be used as part of the environmental impact statement. And so this black line represents the basin for Steptoe Valley. And this black line actually represents the hydrographic divide that goes along a mountain range on the left and right side of Steptoe Valley. And the model that we built, we ended up putting the model boundary as shown by the red line in the interior. And the reason for that is that we were simulating groundwater flow in the basin fill at the center of the valley, and not, most of the mountains surrounding this are primarily bedrock. They have some shallow groundwater flow, but it mostly provides runoff either through streams or just lateral inflow into this valley. And so on the left here, we have, again, the red line is the model boundary we selected. And when you have a case like this, we determined that there's probably substantial lateral inflow as you get snow melt and runoff from these surrounding mountain ranges. And some of these mountain ranges are very high. Mount Wheeler is directly adjacent to this. The Great Basin National Park is close by. And so you get runoff, but you also, in the shallow sediments at the base of the mountains, you get subsurface flow that comes from the mountains into the valley fill. So how on earth do you go about estimating that? We essentially looked at precipitation and did basically a hydrology model. We used something called Maxey-Eakin coefficients, looked at average precipitation, and then, as shown on the right, we divided each of these regions surrounding the model into 8 different zones. So actually 9 mountain zones, 0 through 8. And then using some modeling tools, we estimated how much lateral inflow there would be to the model from each of these 8 regions. And so that lateral inflow was applied to these two sides, and then on the north and the south, we just did fixed head boundaries, and those were far enough from the regions of interest that we didn't think that would cause too much of a problem. And then this is shows the model grid. This is the model on the left is the one we used to calibrate the model and got pretty decent calibration. And then the one on the right is the model we used for some of the predictions we did. By the time we got around to doing the predictions, they had focused on this region up here where they decided they would be the ideal place to put this power plant. And so we calibrated the model. On the left you see the distribution of hydraulic conductivities. On the right you see the head values in the model domain. And then during the predictive phase, we had a series of wells in these locations shown. So this yellow squares here you see are the property boundary where the power plant would be located, and they'd be pumping groundwater. And so what you're looking at is the water levels after the site had been pumped for a while. For this particular case, and ran a bunch of different scenarios. So that's how we went about picking boundary conditions and setting this up. I'm also going to mention that this project never was built. During the environmental impact statement, they looked at there was a lot of concern about having a coal-fired power plant so close to a national park. And ultimately, on the basis of that, is one of the primary reasons this project was killed. I actually agree with that. I think that's probably a wise decision, not putting a coal-fired power plant adjacent to a national park. I think that's a pretty wise decision. But this was a really interesting project to work on. Here's another one. This is one that I've talked about before. This is a model of the Sacramento region right in the center of the Central Valley in the heart of California. And this is a project we did for the city of Roseville, California. And they had a number of objectives for this, but this on the right, you'll see the city of Roseville is right here inside this region. This is Sacramento down here. That's the capital of California. And this was a big project. We worked on this for at least a couple of years. And there were a lot of stakeholders and a lot of things going on. So this red line represents the boundaries conditions that we ultimately selected. And we had the Bear River on the north, the Feather River, Sacramento River, and the Molocumna River on these sides. And if you look at this, you'll notice that when we initially were going to build this, we were going to use this river right here as a boundary and just do this northern part. But there were water districts in this whole region that wanted to be able to use this model for a number of different decision-making scenarios, so we decided to extend it to the south. But any one of these rivers could have been a boundary condition, but we ultimately extended it all the way down here just to cover the set of regions that we wanted to cover. And then on this side on the right, we ended up the right side of this is the Sierra Nevada mountains. So this is a bedrock outcropping on the right. So that and we ended up representing that as a combination of no flow and specified flow boundaries. This is the mountain front recharge that we talked about in these slides. And so how did we go about estimating that? On the right, you'll see the results of a model we built. There's a watershed runoff model called Geisha, GSSHA, gridded surface, subsurface hydrological analysis. I think that stands for, it's a U.S. Army Corps of Engineers model. And we ran this model, and this will give you runoff. It also gave us an estimate of recharge into the system. But we ended up, as shown on the left here, so we have these, and I mentioned these in one of my earlier presentations on this boundary condition analysis series. So we had these adjacent basins 1 through 7 that are just upstream, up in the mountain range, feeding into this valley floor, this alluvial system in the valley. And we used the results of geisha to calculate the runoff that you'd expect from these, and then made that a lateral inflow boundary to the groundwater model. So that's how we came up with that. As shown here by the diagrams. And then once we had the model built and calibrated, we then did this regional to local model conversion at a number of different locations. This is one around the city of Roseville, in order to look at the impact of some aquifer storage and recovery systems. And in one case, they had a landfill where the landfill was, there was a fire burning underneath it, and they wanted to do some groundwater analysis around this crazy landfill that they'd been dealing with for a while. But so basically, we just created this local scale model inside the regional model and extracted the boundary conditions from the regional model, extracted the hydraulic conductivities and the recharge, and then we're able to run this local scale model independent of the regional model. And these are the the head contours for the regional, for the local model, that are entirely consistent with our regional model. So that's these two projects. Again, I like these two examples because they represent a lot of the different types of boundary conditions we talked about. We even got some telescopic or regional to local grid conversion. So hopefully now you have a little better appreciation of boundary condition selection and some of the options available to you, and you should be well suited now to start digging into your projects and coming up with good boundary conditions.